Okay, so the next oscillator concept I'm going to show you here is the Wien bridge oscillator. You can see basically there seems to be a lack of the feedback loop, but in fact, the way to look at this oscillator, that is in fact, it's just a non-inverting amplifier, right, with a controlled closed loop gain. Okay, so the thing to remember about this is that the input and that the cycling that's occurring is occurring on the non-inverting input. Non-inverting input. Okay, so let's tackle the bottom portion first. I'll discuss the non-inverting feedback loop, and this one is very simple to understand. It's basically what we have here is two RC networks, right? And one is acting as a low pass filter, right? And the other one is acting at a high pass filter, or as a high pass filter. So we talked about filters, and what makes a low pass filter is the fact that once you hit your cutoff frequency, right? So any frequencies below it are allowed to pass, and once you hit your cutoff frequency, it gradually decreases. And essentially, a high pass is the opposite. This is as frequency increases, nothing's passed until you get to your cutoff frequency. So the concept here is very much under the band pass type thing. But if you can imagine, what we have here is something set up so that both the low pass and high pass circuits or RC networks have the same cutoff frequency, FC, the same thing, right? Which means that only that frequency, for all intents and purposes, will get through. Okay, so the low pass portion generally in this circuit is the C1 R1 combo, and the high pass portion is the C2 R2 combo. Okay, and we can see that with what is written over here, the fact that we have to find whatever the resonant frequency, you basically need to find total resistance. And generally, we make these values equal, right? So to make this a perfect band pass at critical, you make all these components the same. If you make all these components the same, they have the same cutoff frequency, as stated here. So that's basically all that's really needed to know about this. So the keynote here is the Wien bridge is a non-inverting amplifier. Now let's talk about this negative, or this closed loop feedback network. Now, if the circuit, so let's just imagine for a second that the closed loop circuit is based on the criteria established by these three resistors. Notice that R4 is adjustable. Essentially, that's so we can adjust our closed loop gain or fine tune it. So the way to look at this portion is that you have Rin here, and then you have RF is the combo between these two. That's your return. Let's ignore the diodes for now. So that's your combo. So and then this is a non-inverting amp, so the closed loop gain, it would be just your RF over Rin plus 1. So that's how the circuit would behave normally. Now, where the diodes come into play as if the signal goes more positive, so generally, because remember, we want to keep our closed loop gain to basically, right, we want to keep this criteria. Remember, one of our criteria was that the attenuation times the gain of the circuit must equal 1. So we have a bandpass filter on this side. We have a closed loop network. Well, this is our return network. So what we're trying to maintain is a gain of 1. Okay, so whatever, this oscillator is just oscillating at a frequency, so it basically, once it's triggered, we try to keep it within its set frequency. Whatever comes in, comes out. So I try to keep this closed loop gain basically at 1. If it goes or fluctuates more than 1 by exactly, say it goes more positive by 0.7, this diode shorts out, right? Which would mean at some point we adjust, it would short out, which bypasses R3 and would change the closed loop gain. Okay? If it goes up too high, it would actually reduce, right? RF would have to come down because it would be the sum of those two. So RF would have to come down, reducing the closed loop attenuation. If it went more negative, right? This guy by exactly 0.7, this guy would then short out, right? And again, same effect. It would reduce RF, reducing the gain, bringing it back within balance.